press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about modes of vibration in a stretched string, and important things are fundamental frequency, overtone and harmonic. The lowest frequency with which a body vibrates, right, is called fundamental frequency. Now, the frequencies which are higher than the fundamental frequency are called overtones. Now, the frequencies which are integral multiple of, right, fundamental frequency are called harmonics. These three are the important terms here, and we have discussed modes of vibration in a stretched string, right. So number one, the frequencies of overtones, right, of a stretched string are harmonics of the fundamental. Now, frequencies of overtones of a stretched string are harmonics of the fundamental frequency. Right. That is, we have F1 is to F2 is to F3 is to etc. is equal to 1 is to 2 is to 3 is to etc. Here F1 is fundamental frequency, F2 is equal to 2 times F1. F2 is first overtone, second harmonic, right. So here F1 is fundamental frequency. Now F2 is equal to 2 times F1. It is first overtone and second harmonic. So F3 is equal to 3 F1, that is a second overtone and it is a third harmonic, right. And we know that the fundamental frequency itself is the first harmonic, it is the first harmonic, right. Similarly, we can show that, right, nth harmonic, right, Fn is equal to n into F1, right, where n is equal to 1, 2, 3, etc. an integer. It can never be 0 here. Note that whenever we are having a generalized expression including n, where n is integer, in some cases it may be starting from 0, 1, 2, 3, etc. In some cases 0 will not be there. It starts from 1, 2, 3, 4, etc. If you put n is equal to 1, first harmonic, n is equal to 2, second harmonic, n is equal to 3, third harmonic, right, and so on, right. Now, let us derive an expression for fundamental frequency of a structured string. Fundamental frequency of a structured string. Now, let us consider a string structured between 2 points A and B. So, when the string is vibrating in the fundamental mode of vibration, it vibrates with one loop, right, with two nodes at the two fixed ends and one anti node here. So, this is length L is equal to, this is lambda by 2 or lambda is equal to here 2L. Now, let T be the tension in the string and M be mass per unit length of the string, right. Now, we know that, so fundamental frequency of stretched string in the mode of vibration, we have shown that, right, F1 is equal to V by 2L. But here I will take it as F is equal to V by 2L, because in previous case while discussing modes of vibration, we have taken fundamental frequency as well as overtones, right. Therefore, we need to denote it by F1, F2, F3, etc. But generally, when it comes to only fundamental frequency, it is represented by F, right. Now, here we have also discussed that velocity of transverse wave on string, that V is equal to square root of T by M, equation 2, where T is tension in the string and M is mass per unit length. Now, from equations 1 and 2, it is clear that F is equal to 1 by 2L into square root of T by M. So, this is the expression for fundamental frequency of a structured string, right. Fundamental frequency depends upon length of the string, tension in the string and mass per unit length, and the string can vibrate with different frequencies. The higher frequencies are called, right, overtones, right. So, in general, frequency of vibration of a structured string depends upon tension, length, mass per unit length and modes of vibration. But fundamental frequency particularly depends upon three factors: tension, length and mass per unit length. So, here, so T is tension in string measured in Newton, right. L length of string measured in meter. Now, M is equal to M by L. This is a mass per unit length of string. It is measured in kg per meter. Volume density, that is mass by volume, is measured in terms of kg per meter cube, whereas linear density or mass per unit length is measured in kg per meter. And this is the expression for fundamental frequency of a stretched string. Now, we will take loss of vibration in a stretched string. Yes. Loss of vibration in stretched string. Generally, it may appear in board examination for 3 marks. There are 3 laws of vibrations in a stretched string. They give us how fundamental frequency of vibration of a stretched string, right, depends upon length, tension, mass per unit length, etc. Or these law give how do fundamental frequency, right, vary with, right, tension, length and mass per unit length of this thing. So first law, right, is called number 1. This is first law. This is also called law of tension. It states that the fundamental frequency of a stretched string is directly proportional to square root of its tension, provided length and mass per unit length of the string remain constant. Right. So the statement, the fundamental frequency of a stretched string is directly proportional to square root of tension in the string, provided length and mass per unit length of string remain constant. That is, fundamental frequency of a stretched string is directly proportional to, right, tension in the string when, right, length L and mass per unit length M are constant. Generally, it means to say when L and M are kept constant, fundamental frequency increases with increase in tension, right. That means if the tension is increased by n times, fundamental frequency increases by root n times. Suppose if tension is increased by 4 times, then the frequency increases by 2 times. Suppose if F1 is the frequency at tension T1 and F2 is the frequency at T2, then it can be shown that F1 by F2 is equal to square root of T1 by T2. That means to say when L and M are constant, if we know frequency F1 for any known tension T1. So we can calculate frequency F2 for any unknown tension T2. Right? Now, the second one, it is second law, also called law of length. Now, we take this statement. This law states that the fundamental frequency of vibration of a stretched string is inversely proportional to length of the string provided tension and mass per unit length are constant. Right? So, the fundamental frequency of a stretched string is inversely proportional to length of the string provided tension and mass per unit length remain constant. Right. Now, according to this equation, fundamental frequency F is proportional to 1 by L when T and M are constant. This law gives how does fundamental frequency of a stretched string vary with its length. So, by increasing the length, fundamental frequency decreases. If the length is increased by n times, then fundamental frequency decreases by n times. Right? That means if F1 is the frequency at the length L1 and F2 is the frequency at the length L2, then it can be shown that F1 by F2 is equal to L2 by L1. Using this equation, when T and M are same, if F1 is the frequency for length L1, then we can calculate frequency F2 for any other length, right, L2. Now this is third one. This is called third law. It is called law of mass. Now take the statement. It states that the fundamental frequency of vibration of a stretched string is inversely proportional to square root of mass per unit length of the string provided tension and length remain constant. Yes. The fundamental frequency of a stretched string is inversely proportional to square root of its mass per unit length provided its tension and length remain constant, that is F is proportional to 1 by square root of m, right? That is when T and L are constant, right? So if F1 is the frequency for a wire of M1 and F2 is the frequency for a wire of M2, right? For the same tension and length, we can write F1 by F2 is equal to square root of M2 by M1, right? Generally, in musical instruments, right, the tension can be varied by using the screw at one end of the string, the other end is rigidly fixed. Length of the string is varied by pressing the string at different positions, and mass per unit length can be changed by changing the string, because when we use a string, for depending upon its thickness and length, right, it remains the same. We cannot vary the linear density of given wire, but they are using several wires because they have different mass per, right, unit length. Right. Now, we will take some note points. We know that fundamental frequency of a stretched string 1 by 2L into square root of T by M. Let it be the equation 1. Or this can be written as F is equal to, right, square root of T by taking 2L inside the square root, it becomes 4L square M. That is equation 2. Now, we have mass per unit length is equal to M by L. Right. Mass per unit length is equal to M by L, right? Or we can write mass per unit length is equal to M by L, right? Or this is area into M by area into length, where A is area of cross section of the wire. This is equal to A into M by V, where V is volume of the wire, right? This is equal to A into rho, right? Where rho is density of the string. So therefore, we have F is equal to, right, square root of T by 4L square, right, into A into rho. We'll take it as equation 3, right. Now, we have if D is diameter of the wire, if D is the diameter of the wire, then area A is equal to pi D square by 4L. Therefore, F is equal to square root of T divided by 4 L square, not, this is pi d square by 4l, right. And now this is 4 L square into pi d square by 4, right. So f is equal to square root of t by, right, this is this area m by l into volume, right. This is 4 that means from this one 4 get cancel, so we can write the fundamental frequency is inversely proportional to, right, 1 by square root of d, or it is 1 by d, or fundamental frequency is proportional to, right, 1 by square root of rho. So fundamental frequency is inversely proportional to square root of the density of the wire, and fundamental frequency is inversely proportional to diameter. That means as the diameter increases, the frequency decreases. For same length and tension, a thin wire has more frequency and a thick wire has less frequency. Now, so far we have discussed about vibration in a stretched string. Generally, the sounds produced by musical instruments like veena, guitar, sitar, violin, etc. are due to transverse vibration of a stretched string in them. When a stretched string is set into vibration, a transverse longitudinal wave is produced in the string, right, consisting of nodes and antinodes. But that transverse vibration in the string produces disturbance in the air. The air particle began to vibrate with the same frequency of the transverse stationary wave, and sound is produced, that is a musical sound, and it reaches the ear. So the vibration in the string of musical instruments, stringed instrument, is transverse, right, mechanical vibrations, transverse mechanical wave, whereas the sound produced by these strings are longitudinal mechanical waves, right. Clearly, in strings, wave is a transverse stationary wave, but sound produced by string is longitudinal mechanical wave, right. Now we will take another one, it is air column, right. So a column of air enclosed by a cylindrical pipe or a tube or any enclosure is called as an air column, right. A column of air enclosed by a cylindrical pipe or tube or any enclosure is called an air column. For example, we can take flute, right? A flute is an air column because it encloses air inside it. It is a cylindrical shaped, right, tube or pipe. Even that shahanai, trumpet, and generally when we blow air to a pen cap, we can produce sound, that is visual, we say that. So when somebody produces visual in his mouth, right, the mouth also acts as an air column, right? So that's why we can able to produce, and these instruments like flute, shahanai, trumpet, etc. are called, right, air instrument, right? Here the vibration is not the entire air, only those air enclosed inside the cylindrical tube, right? So here we use two types of pipes. There are two types of pipes or air columns, right? Generally they are called pipe, right? Flute, shahanai, etc. are called organ pipes. They are used to produce musical sounds, right? So here generally we call it as, right, pipes. There are two types of pipe. One is open pipe, right? A cylindrical tube whose two ends are open is called an open tube. So here this is an open tube, right? Now when we take the flute used by professional musician, right, you might have seen the flute used by Lord Krishna in Vrindavan, right? It is an open pipe because it is open at both the ends, right? And we have number two, closed pipe, right? A cylindrical tube or pipe which is open at one end and closed at the other end is called as a closed pipe. It is like that. It is a closed pipe. One end is open, the other end is closed. The most suitable example for closed pipe is the cap of our pen, right? Suppose if it is cylindrical in shape, right, then its one end is closed and the one end is open. When we just blow air into that pen cap with suitable speed, then visual is produced, right? That is, sound is produced. That is due to the vibration of the air enclosed inside the pen cap, right? You got my point, right? Now we'll take modes of vibration in an open pipe. Modes of vibration in an open pipe. Now let us consider an open pipe of length L. Let us consider an open pipe of length L. I have taken it here, right. Now this has the length L which is open at both the ends. When a vibrating tuning fork is held at one of the open ends of the pipe, longitudinal sound waves, they propagate along the length of the string in the form of alternate compressions and rarefactions and get reflected from the other end, right? Here there is no change in medium, but there is a change in pressure. Now outside air is at atmospheric pressure. When sound propagates through the medium, the pressure at compression is more than atmospheric pressure. The pressure at rarefaction is less than atmospheric pressure. Therefore, when a compression comes at the other end, now this is at higher pressure and outside air is relatively at lower pressure. As a result of pressure difference, right, the wave get reflected, right? Or when a rarefaction comes here at the lower end, then it has lower pressure relative to the outside atmospheric pressure. Due to that pressure difference, the wave get reflected. One thing here, since there is no change in medium here, right, due to pressure difference reflection takes place, the if compression incident at the lower end, it is reflected as a compression. There is no phase difference between incident wave and reflected wave. If a rarefaction is incident at the other end, then it is reflected as a rarefaction. So, this reflected wave is identical to the incident wave, right, but traveling in opposite direction. So, the incident wave and reflected wave, right, they superpose on each other, forming a stationary wave, which is a longitudinal stationary wave, right. Now, since the open end, right, at the open end, the particles, air particles have maximum freedom of vibration. Therefore, antinode is always formed at the two open ends. Now, this is like that. Right. So, two antinodes are always formed at the two ends because antinode is a particle vibrating with maximum amplitude, and here now the particles have maximum freedom of vibration here. Now, here a node is formed between them. Right. Now, if F1 is fundamental frequency, right. Now, so see here before taking that frequency. Now, this is called the first mode of vibration. The first mode of vibration or fundamental mode of vibration, because the air column is vibrating with, open air column is vibrating with the minimum possible number of nodes, because two antinodes are always formed at the open end and a node should be formed between the two ends. So, here the number of nodes and antinodes formed, one node and two antinode, right. So, in the fundamental mode of vibration, an open pipe or an open air column vibrates with one node and two antinodes, but in stretched string it is two node and one antinode, because at the two fixed ends the particles of the string cannot vibrate. Therefore, at two ends of a stretched string, nodes are always formed. But here, in case of open pipe, two antinodes are always formed at the two open ends, and of course a node between them, right? Now this is first mode of vibration. Now, so here if F1 is fundamental frequency, F1 is fundamental frequency and lambda 1 is fundamental wavelength, then we have V is equal to F1 lambda 1 or F1 is equal to V by lambda 1, where V is velocity of sound in air, because the sound waves are propagating through air, where V is velocity of sound in air. Now, if two antinodes are forward, now the distance between two antinodes is equal to lambda 1 by 4. Remember that distance between lambda 1 by 2. Remember that distance between two successive nodes is lambda by 2. Two successive antinodes is lambda by 2. But the distance between a node and an immediate antinode, right, is lambda by 4. So here it is lambda 1 by 2. Therefore, that value of L is equal to, right, this is L is equal to lambda 1 by 2 or lambda 1 is equal to 2L. Therefore, right, this fundamental frequency F1 is equal to V by 2L. Let us take it as equation number 1. So, fundamental frequency is equal to V by 2L, where V is velocity of sound in air and L is length. Right. Now in the next mode of vibration, right, what happens? One node and one antinode increases. That means here, instead of two antinodes, we are having three antinodes, and instead of one node and we are having two nodes. That can be represented like this. Now the pattern is like this. This is antinode, node, antinode, node and antinode. Now, so as the mode changes, this is called, right, the second mode of vibration. And second mode of vibration has higher frequency, right? Now, if F1 is, right, frequency of first overtone and lambda F2, lambda 2 is wavelength of first overtone, then we have V is equal to F2 lambda 2 or F2 is equal to, right, this is V by lambda 2. Now here we have up to this distance it is lambda 2 by 2, up to this distance it is lambda 2 by 2. Therefore, the total distance between the first antinode and the third antinode, right, it is lambda 2. To here lambda 2 plus lambda 2 by 2 plus lambda 2 by 2, lambda 2, right. Therefore, right, So V is equal to, right, when F2 is equal to, right, V by L, or it is equal to 2V by 2L. That means F2 is equal to 2 into V by 2L, right. That means F2 is equal to 2 times F1, equation 2. That means the frequency of the first overtone is same as the is 2 times the fundamental frequency. Therefore, F2 is first harmonic, F2 is first overtone, and it is equal to second harmonic, right. Now remember that equation. I will take this here. So F1 is equal to V by 2L, F2 is equal to 2 times F1. Now right, in third mode of vibration, we have 3 nodes and 4 antinodes. The pattern will be like this. This is length L, this is antinode, node, antinode, node, antinode, node, and antinode. Now here, see, this is third mode, second mode of third mode of vibration. Now if F1 and F3 and lambda 3 are frequency and wavelength of second overtone. First mode fundamental frequency, second mode first overtone, third mode, right, second overtone, right. Now we have V is equal to F3 lambda 3, or F3 is equal to V by lambda 3. Now here this distance we take. Now this is this distance lambda 3 by 2. This distance lambda 3 by 2 and this distance lambda 3 by 2, that is 3 lambda 3 by 2. Therefore, L is equal to 3 lambda 3 by 2, that implies lambda 3 is equal to 2L by 3. Now this frequency of 3 is equal to V by 2L over 3, that is equal to 3V by 2L, or F3 is equal to 3 into V by 2L, or F3 is equal to 3 times F1, equation 3. So F1 is equal to V by 2L, F2 is equal to 2F1, right. This is equation 1, this is equation 2, right. Now from equations 1, 2 and 3, right, F1 is to F2 is to F3 is to etc. is equal to 1 is to 2 is to 3 is to etc. It is very much similar to the vibration, modes of vibration in structure string. That means we say that the frequencies of overtones of a stretched string are harmonics of the fundamental frequency. That means here we have all the harmonics present, both odd harmonics and even harmonics are present here, right? So we shall conclude the class at this stage. In the next class we will discuss modes of vibration in closed pipe and one or two concepts related to modes of vibration in air column, right? Thank you very much.